Hi, I'm Travis Shy.
I'm Annalyn Edulog.
I'm George Bowler.
Welcome and thank you for joining us for our senior project Shoe Sole Tester. So for our agenda today, we will be going over our project purpose, the design research and development, then go into detail over major subassemblies, discuss costs, and end with future work and conclusions.
First, we want to establish the purpose of this project. The primary intent of this project is to standardize and streamline the footwear testing process. Our goal was to design a machine that could accurately replicate the average human gait when both walking and running. In this effort, we first did some research to see where there may be existing products to innovate and improve upon. First, we looked at the Helix Time Machine Shoe Tester. This machine utilizes an 80-20 extruded aluminum frame attached to a modified treadmill. While this design is innovative, it would be difficult to mass produce repeatably, and it is also larger than it probably has to be. Second, we looked at the Satra Peditron. This machine is more of an industrial design, intended for testing footwear in different weather conditions. This machine is very robust, but also very expensive, and it would be hard to market to our intended audience. With all this in mind, we developed the following design requirements. Our first priority was designing our system to replicate as closely as possible the average human walking and running motion. Next, we decided to cap our overall manufacturing budget at $6,000 in order to stay well below some of our competitors' prices. We also decided to design all of our components to a minimum factor of safety of 3 in order to make the machine durable enough to wear through many pairs of shoes. Also, we decided we wanted to limit our overall form factor to a 3 foot by 3 foot square in order to minimize floor space taken up by the machine.
So for our initial design, we first implemented a DC motor that is connected to a gear reducer by a belt drive. We also included a planetary gear drive that collects the leg linkage to move up and down and is guided by a two-way slider. For our motion, the leg would also hit a rotating base, and a leg spring support was included to dissipate the energy. So for our final design, on the left you can see that it fits within the design requirements of fitting within a 3 foot by 3 foot space. On the right side, you can see our final design in motion with all of the updated components, where Travis will highlight the major subassemblies next.
All right, so for the final design, it can be broken down into these highlighted subassemblies where the horizontal beam in blue holds most of the components and is hinged at the end to the fixed vertical supports as highlighted in green, with a spring support on the opposite end. Highlighted in purple is the leg linkage system with the rotating base positioned directly below it, and the mounting plate in red on the bottom was designed such that all the components could be easily fastened with accurate positioning. Next, we'll go into more detail for the structural supports. So on the double T-slot aluminum beam, we have a 2750 RPM speed control motor connected to a 10-to-1 gear reducer. On the other end of the beam, we have a lead weight plate, which was used to increase the overall weight acting on the foot in each step. Additionally, a counterweight was added to balance the weight of the leg linkage and step actuator in order to reduce eccentric bending stress in the beam cross-section. And the spring support was designed to move upward with the beam as the foot makes contact with the ground and utilizes a linear compression spring to dissipate energy as it comes back down. For the analysis into the horizontal beam, a static FEA simulation was conducted modeling the weight of the components as distributed loads. For the results of this analysis, it was found that the maximum von Mises stresses were around 2.4 KSI with a yield strength around 39.9 KSI. And considering the vertical displacement of the beam, this was found to be approximately 0.02 inches, which is fairly negligible. Next, for the spring support analysis, this was mainly constructed from alloy steel tube and shaft, and a static FEA simulation was conducted, resulting in maximum von Mises stresses of 1.3 KSI with a yield around 50.9 KSI.
Next, I'll be going into the subassembly of the leg, ankle, and foot. So for the leg beam, it's a piece of two-slotted 80-20 aluminum. We first performed theoretical calculations based off a compressive force of 200 pounds. So while the leg is in motion to achieve the heel-to-toe strike, the compressive force acts at an angle at about 70 degrees, as you can see in the figure below, which causes a bending stress. However, based on the calculations, the maximum stress applied is due to the compressive force at a value of 253 psi, which is below the yield strength of 39 ksi for the aluminum alloy. Next, we did a static FEA analysis, which was performed with a 200-pound compressive load, and the von Mises stress was below the yield at about 368 psi. So for the design of the foot, it was based off average foot dimensions. We utilized a shoe size of a US 10.5 and a width of 4 inches. And also the dimensions between the base of the foot and toe component were influenced by biomechanical research, where it was determined that a ratio of 22:1 output the most human-like gait in simulating machine walking. It was also determined that torsional springs are comparable to the functionalities in both toes and ankles. So based on the foot, we performed an analysis to determine the net forces caused by the applied 200-pound load on surface conditions of asphalt and concrete. It was found that the greater the surface friction, the greater net resulting force would be. And based on this, assuming that the manufactured foot would be made out of 6061 aluminum, it will be able to withstand the forces applied. Also, the torques on the toe base were found based on the length and the net forces, which will be beneficial as a baseline when rating the torsional spring. And it's also important to note that all the springs used will be tested when a prototype is developed.
Next, I will be talking about our rotating base subassembly. This design is centered around the rotating cylindrical platform on top of the base. This cylindrical platform is our stepping surface. The one shown here is made of 1-inch thick concrete. It is designed in such a way that it could easily be switched out for a walking surface made of asphalt, hardwood, or any surface desired. The platform rotates at 5 RPM to ensure even wear upon the walking surface. The lubricated turntable the platform sits on is driven by a motor mounted on the underside of the table. This is a relatively simple design. I'll go into some more detail on the stress analysis conducted on the base on the next slide. We determined the maximum load the base would encounter would be about 210 pounds, with 10 pounds coming from the concrete base and 200 coming from each step. The base was designed in such a way that force is translated directly from the top of the step surface through the vertical columns and into the floor, without putting very much stress on the joints. In the end, the base was determined to encounter a maximum stress of 100 psi, which is well below the yield stress for aluminum.
Next, going into the dynamic analysis, the dynamics of the leg linkage can be simplified into a conversion of rotational speed from the gear reducer to the linear speed of the leg by keeping a fixed center-to-center distance of 3 inches. The specifications of the motor and gear reducer were determined from an iterative process which yielded walking and running speeds within the averages found in literature as seen in the table in the top right. Also, by maintaining operating speeds between 60 and 100% motor power, this should maintain lower gear stresses by operating at a higher range of speed. Next, we'll go through the critically loaded shafts, which are highlighted in the picture on the right. For the critically loaded shaft analysis, all the shafts used throughout the design were assumed to be machined steel. For the hinge shaft, a static FEA simulation was conducted using a 154-pound compressive load, which essentially equated to the weight of the horizontal beam and the components attached to it. This simulation resulted in a von Mises stress of 7.4 ksi, with the yield far greater at 50.9 ksi. For the output gear reducer shaft and the leg linkage pin shaft, theoretical fatigue analysis calculations were conducted based off their alternating stress components and were found to have factors of safety of 5.78 and 3.51 respectively.
Here we have a cost breakdown of our design. Some of our most expensive components were our motors and speed reducers. There are some possible savings here, however. McMaster-Carr can be a bit expensive for certain components, and bulk ordering can lower some of these costs significantly. All in all, we found our overall cost to be under our limit of $6,000.
Going into the future work that can be done on this project, the first thing would be to build a physical prototype to test for component functionality, as well as conduct several tests using various conditions in order to gather and quantify shoe sole wear data. Additionally, An optimized analysis can be done on parts with high factors of safety to help reduce oversized components. Some other areas of improvement might be to make a stationary redesign of the spring support or possibly add an apparatus to simulate wet weather conditions on the walking surface.
In conclusion, our design was feasible in terms of size, cost, factor, safety, operating time, and speeds. It was also inspired by biomechanical research in order to replicate a human-like gait, and developing a prototype would allow for further optimization and redesign as necessary. We would like to say a special thank you to our advisor, Dr. Azai, as well as Cal Poly Pomona's mechanical engineering faculty. These are the references we use. Thank you for listening. If you have any questions, please feel free to email us below or ask us during our live Q&A.